In my first lecture, one at least of you, and quite one of the smallest, may I say, was smart enough to spot that there was an error in one of my slides. It was the one which had the Roman figures on it, and you may have noticed there was a D, which really should have stood for 500, where it should have been an L. I'm sorry for that. And I've also found that the caricature of the Roman writing down 1,000 M's wouldn't have occurred probably in later Roman times, because by that time, some at least of their mathematicians had realized the need for bigger numbers than 1,000. It's true they hadn't got a word for any number bigger than 1,000, but if they put a bar over the top, for example, M with a bar over the top, would mean 1,000 thousands, in other words, a million. But the main point, that they hadn't got the zero sign, is still true. You may also have noted that through some, I can only explain as a Freudian slip, I said that we divided our inches up into eighths, sixteenths, 32nds, and for some reason or other I said 65ths rather than 64ths. I can only think it was a Freudian slip because in good Scottish bars, whiskey is sold in fourths as opposed to English bars where it's sold in fifths of a gill. I don't know whether that's the explanation, but anyway, I apologize for the mistake. Now, today I'm going to talk primarily about how we measure large distances, and in particular to distances to objects that we cannot actually approach. But before I do that, there are two things that I'd like to do first. And of these, the first is a very simple demonstration of what was really a very important experiment. And for this, I'd like a volunteer, and I think here he'll come out. And the situation is when Lord Rutherford had found that there was a particle, his beloved alpha particle, and that normally, as with high-speed particles, it travelled in straight lines. And if you like to show how an alpha particle running down here would travel in more or less straight line, well, that was a good shot. It really went in there like that. Try one from this end too. Well, that was nearly bang in. Well, then that was exactly the sort of thing that Lord Rutherford expected when he fired his alpha particles through matter. The situation, I think, is portrayed on the first slide. You can have it there. And you'll see he had his source of alpha rays. He then fired through a hole in a screen to define their direction. And he then fired them through gold foil. And at that stage, people had some idea of how big atoms were, but they knew that they were packed together closely in solids, and what he imagined perhaps was that the alpha particle would go through, rather like would go through a bag of sawdust, and come out the other side rather slowed up. But to his amazement, he found that most of them went through just as straight and just as unaffected as though there was nothing there. The answer was there was nothing there. But he also found that every now and again, if he dropped past one like this, it didn't go, well, we'll try one for the other side there. But now try one from this one here. And we can try one or two more. that merely accelerated it. And what Lord Rutherford, whose picture is on the next slide, said that this fact, and let's try one for one of the good ones again, or here, I think, here. He said that fact that every now and again his counters showed particles coming off at quite an acute angle. We can try one or two more while we're talking. And it's quite obvious there's some source of disturbance here. In fact, it's a large magnet underneath. You see, oh, it's a beauty, yes. Well, thank you very much. That's shown the idea perfectly. And actually, it's all right when you know the explanation, but it took Lord Rutherford some months before he forced himself to the conclusion that, in fact, what was happening was that most of the atom was completely empty and that there must be some very hard deflecting core in the middle of it, which he called the nucleus. And the point I wish to make is this, that I've been talking about what you can do with really precise measurement. And yet here, what we've seen is how the big idea, such as the nucleus, came from just this very simple qualitative experiment of finding that sometimes alpha particles came off in a quite different direction from what you'd expected. Rutherford said it was as staggering to him as though he'd fired a 15-inch shell at a sheet of tissue paper and the shell had bounced back. That was how his own words are how he put it. So how is it that every now and again one of the really big ideas in science comes really, as it seems, with no measurement at all? And yet at other times, very precise measurements indeed have been needed. Well, for this, I'd like to go back to the slide that we had in an earlier lecture, where we had this scheme for making an automatic reading scale where photocells behind here would detect any particular position. Now, what that very crude experiment could be classed as sorting between this set of possibilities and that one. It could be phrased as a question which demanded simply the answer yes or no, are alpha particles deflected or not? If they are, it turns out there must be a nucleus. Of course, if you want to find how big the nucleus is, or really, in fact, how small it is, what you've got to do is to fire an enormous number of particles, take count of every one of them, and measure the angle at which those which are deflected come off. And this, of course, is what Rutherford then did. And he found that the nucleus was only about 1/100,000th of the diameter of the atom. A very small body indeed, right at the middle, with almost the whole of the rest empty space. But to get the idea, almost no measurement. First I'd say no measurement, but in fact it was the first stage of measurement when you sort into all the possibilities into which half the answer lies, yes or no. You've got to do then much more refined experiments to find just how big or small the nucleus is. And you then see this power, incidentally, at the scale of 2. And those of us who are old enough to remember those panel games like What's My Line or 20 Questions, which always amazed us by the way in which the panel got time after time the answer. You see, if you have 10 questions and you only have no help from the question master, nothing from the tone of voice, but merely yes or no, in as impartial a way as possible, you can, with well-designed questions, sort out any one of 2 to the 10th, which is 1,024, professions in What's My Line, or in 20 questions, 2 to the 20th, which is over 1 million. So when you realize this, and it's exactly the same in government or in military organization or anything else, as Churchill himself said, the job of the man at the top, the general, is to decide right or left, advance or retreat, or in the case of a prime minister, increase taxation or decrease taxation. They're the big decisions, and at lower levels, the details have to be worked out. Well, I wanted to show you, because you know I'm talking so much about precise measurement, that really sometimes very crude experiments are very important, but they're not really different. They're merely the first step on the ultimate road to precision. The other subject I want to talk about before we actually get to determinations of distances of distant objects is one of the most important phenomena in the whole of physics, and that is the velocity of light. Now, the velocity of light turns out, as far as we can tell, to be a constant under whatever circumstances one measures, and it was part of one of the basic assumptions in Einstein's theory of relativity that everyone would get the same answer for the velocity of light, and one can in fact determine it now so very accurately by various techniques that it is one of our basic standards, and the time could come when, instead of using atomic wavelengths as units of length, because we know the velocity of light so precisely, and because we also know that we can measure time so very precisely as we've seen, that we may, in some future time of some future year, redefine our unit of length as the distance travelled by light in some particular time. Well, we haven't quite arrived there yet, but that is one of the possibilities. And it is indeed very important in what I'm going to talk about in the measurement of distance. And for that, I want to give you one or two illustrations. It's very difficult to do an experiment inside a lecture room which shows some positive effect due to the fact that light takes a definite time to cover a definite distance. But now, owing to modern technology, space technology, and the skill of the BBC engineers, the collaboration of the BBC organisation in New York, and the engineers in British Telecom, we're going to try and show you a positive effect because light takes so long, not very long, but nevertheless an appreciable time to travel. What we're going to try and do is this, that here in England, we're going, in fact, from that telephone, we're going to try and telephone New York via a satellite, a communication satellite. Now, that is a satellite which flies in what we call a geostationary orbit. That's one over the equator. At such a distance, the satellite goes round at exactly the same rate as the Earth does, so it stays in the same position. And for that, it has to be about 22,000 miles out, somewhere out here, shall we say. Remembering the diameter of the Earth is 8,000 miles, so it's almost 3 diameters out. The message will go up to this satellite, then back into the New York office of the BBC, and then they're going to plug the two lines together, having also telephoned us. It should come up on that line there. So the message, which has gone like this, down there, will then come back again via the satellite and back there. So it's going to do 4 times 22,000 miles. In other words, 88,000 miles. Almost, remember, the velocity of light being 186,000 miles a second, it'll take almost half a second to do it. And so if the conditions are right and our luck holds, Mr. Coates will now telephone New York. And the BBC office in New York will then telephone, we hope, here. Are we getting ringing tone, Bill?
Hello? Hello, could I speak to Mike Hill, please? BBC office.
Mike Hill.
Hello, Mike. Bill Toast here, the Royal Institution.
Oh, good, hello.
Hello there. How are you?
Well, thank you. And yourself?
Did you have a good Christmas?
Yes, thank you.
Tell me, what's the time in New York now?
The time in New York is now just coming up for 10 past 10.
That's at night ago.
No, that's in the morning.
In the morning, of course, sit down.
Day with blue sky and a few fluffy clouds about, and it's quite warm outside. It's about 35.
Okay, well now I wonder if you could ring one of my assistants. She's rather a glamorous one. It's Melanie on the phone number you have.
Melanie?
Yes?
Right. One moment.
Now, the thing to do will be to watch the lips anyway, so that you see the sound coming out, and you'll hear it come out of the other telephone. We hope the whole thing will come onto the public address system, so that you'll be able to hear both.
Hello, Mike. It's Melanie.
Hello, Melanie.
Hello? How are you?
Hello, Mike Hill here.
Nice to meet you on the phone. I gather you're going to let Bill speak to me, and then I have to say some nursery rhymes so we can hear the time delay.
That's right. If you just hold on a moment,
Thank
I'll
you.
connect you two together.
Thank you very much.
Now, go ahead.
Okay, Mike. Hello, Melanie.
Hello, Bill.
My gosh, you sound a little way away.
I've just got you there, Bill. How are you?
Oh, I'm doing very well, thank you. By the way, Melanie, can you remember any poems from your childhood?
I think so, Bill. I'll try. Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, the lamb was sure to go. Now, Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. Can you hear me, Bill?
Yes, very well indeed. Can you hear me still?
Just, yes.
Just. You can
You've
see
just
me,
got
can't
to
you?
me. Do you want another nursery rhyme, Bill?
Oh, have another one as you wish, yes. The BBC are paying.
But I would like to...
Mary had a little lamb again. Have you had enough?
Carry on.
Mary had a little lamb whose fleece was white as
Are
snow,
we getting
and
delay?
everywhere that Mary went, the lamb was sure to go.
Yeah, I'm getting it.
I'm very short on nursery rhymes, Bill. I'm sorry. I'm going to have to go
Yes.
through them again.
But what we would like to hear is so you're speaking in, we'd like to hear it coming out on this telephone, and I'm not sure that the audience can hear it.
Not getting it.
Carry on. Jack and Jill went up the hill.
You can hear the delay, can you?
Carry on.
Yep.
Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after.
Right, thank you very much. Well, thanks to everyone involved in that very complicated link-up, both in the Royal Institution and the BBC and British Telecom. And you can now say that you've actually heard a positive effect of the fact that light does not travel quite with infinite speed. And there is another illustration that we can show you, or let you hear, and that is that once radio transmitters became so very powerful and can be directed so effectively, and also receivers were so very sensitive, it has now, for perhaps the last 20 years, been possible to talk to the moon, or at least to talk to oneself via the moon. And we have a record thanks to Jodrell Bank, who directed their great telescope at the moon, and you can hear the observer saying hello, and his voice being transmitted on the radio waves out to the moon, roughly 250,000 miles away. So the return journey is 500,000 miles, and the speed of light, remember, is just under 200,000 miles a second. So it's about 2.5 seconds. And if we could have the record... Or
Hello, Moon. Can you hear me? Hello, Moon. Can you hear me? Hello, Moon. Can you hear me? Hello, Moon. Can you hear me?
That's what, there we are. And so we can use, you see, in that particular case, if we didn't know the distance to the moon, but knew the speed of radio waves, we can estimate how far the moon is away. And we should be talking about this because it's really the basis of radar later on. But I want to talk about more elementary ways of determining distance for a start. And one of the basic ways, since light can be, for these purposes, be regarded as travelling in a straight line, is to make use of the properties of similar triangles. Now, supposing that I take these triangles, and you see there is one, and I want to make a bigger one, the shape of the big green one over there. I can do this by this. What I've got to do now is to add another 3, like that. And we've got now a triangle of exactly the same shape as it was before, but it's now 4 times as big in area. The sides are each twice as long. We'll go on to do 3 times as long, like that. And with 9, we can now make a triangle whose sides are in exactly the same proportion as these were, but the whole thing is 3 times bigger. And therefore, if we can establish the angle here and that length, it will be exactly the same ratio as for of this distance to that distance as it was from this to that. And so we can reduce our big problem down to something inside our laboratory or our observatory by the properties of similar triangles. And I happen to use a 30-degree triangle, but it's true of all triangles. And one possibly useful tip is that quite often you want to find the height, get some estimate of the height of a tree, and at the top of the Christmas tree there should be a little light. What I will do, had there been more time, we would have done this experiment seriously, but the moon was obviously a far more interesting thing to hear and the satellite to talk through. But you can always make a 45-degree triangle just by folding a piece of paper like that. And you know that side is equal to that side. And therefore, if you took this triangle and kept that side horizontal and sighted along there like that, I would know that the distance from my eye to the tree is the same as the height from this level up to the top of the tree. And so all I've got to do is to paste this out like that, if I wanted to, or step it out with a big tree, take that length, add on the height I'm above the ground, we've got the height to the top of the tree. Or if you're skilled enough in judging angles, you could do it even without the bit of paper, at the risk of being judged a Nazi, if you just held your finger up at 45 degrees and walked like that. So in this way, you can get a rough idea of the height of a tree. And the method can be used much more exactly by means of the device called the rangefinder, which was developed about 100 years ago by Professors Barr and Stroud. And we have here a system which simulates the rangefinder in this way. We have a small lamp, which should be alight any moment, and some of the light from the lamp comes this way and goes through a green filter, so it throws up a beam of light, shaded green, up here. That mirror is roughly 45 degrees. This mirror is also roughly 45 degrees, but in this side there is a red filter. So the light coming on from here is red, And if the mirror here is at the appropriate angle, the red beam and the green beam will cross there. Whereas if it's tipped over like that, they'll cross there. So if one wants to find the range of that point, what you've got to do is to swing this mirror until the two images, which otherwise be separate, cross. And what we'll do is to try to measure the height of the lecture room. And for this, I could do with a volunteer. Philip, you come down. And what we're going to do, the movement of the mirror is very small, but we're going to magnify it up by a very simple gearing here. And we'll need the lights down, because otherwise we won't be able to see this slender beam. Ah, yes, now we can begin to see them. Do you see there's a red image and a green image up there? And if one works his handle correct, it's a bit tricky, one will get them into coincidence. Well, and in this way, you see that? Just move this and try and get them. Well, it's pretty good. It's pretty good straight away. One will also see where they are in coincidence, by the way, that the red and green superimposed give a yellow because the eye is tricked. Its red receptors and green receptors are triggered as though there was a yellow on them, and the brain interprets it as yellow. Now, what we can do now, Philip, if you'll look round here, we can measure the height of this scale. If you come round here, we can measure the height. Just about 40 feet. Thank you very much. And the system was used, you can always use anything in optics either way round. Light will always retrace a path that it's travelled in one direction. And in the rangefinder, of course, we don't use beams like this, visible beams. We look at the distant object through mirrors at opposite ends of baseline. And the clever thing about the Barnes-Stroud rangefinder was that instead of trying to tilt this mirror, as we've done, where the angle is very small, particularly for very long range determinations, a very shallow angled prism is put in the path of one beam, and it's moved along here like that. And that has the same effect. But because this is, you get such a large movement here for a very small change in angle there, it becomes a very sensitive method of range finding. And indeed, one of the original Barnes-Stroud rangefinders is here, and one had to look in through the eyepiece and see the image, and instead of superimposing a red and green as we did there, the image is split. Just as in the cameras that so many of you have, the range finding is done by making one image move past the other until the right points come into coincidence. Well, that was the Barnes-Stroud rangefinder, and of course, once invented, it was developed. It was the main method of range finding in navies up to the advent of radar. And you can often see, if you look at the photographs of World War I and World War II battleships, a great seeming bar out on the conning tower, and this was the rangefinder, taking every advantage of every inch of separation that you could obtain. Well, the method is extremely useful, and we use it still as our prime method of determining the ranges of stars. And if I could have the next slide, this will show the situation. There aren't many stars which are close enough for us to use the biggest rangefinder that we can make, but there are some. And the biggest rangefinder that we can make and take for a baseline is in fact the orbit of the Earth around the Sun. 93 million miles to the Sun, so 186 million miles across. And since the Earth moves round the Sun in an approximately circular orbit, if we got a star in any direction, at some time we will have our baseline facing in the right direction to produce the biggest change in apparent angle at which we see the star. Now, I've said most stars are well beyond that range. In a way, this is almost a help, because it means that if you take two photographs, say at 6 monthly intervals of the sky, most of the stars will be so far away they still seem to be in the same direction. But the closest stars will appear to have moved, so that if you have two plates and superimpose them on one another at some months interval between, most of the stars will be in the same position, but a close star will appear to be in a slightly different direction in the two different times. And there is, fortunately, a very quick way of spotting any such star, and that is to have the two plates, one in front of each of your eyes, and the light move from one to the other, so that when there's no light there, there's light there, and vice versa. So light was coming through from a star image here also coincides with light coming through from a star image there on the other half, and you see the star in a constant position. But any star that's moved its position, it will be illuminated here at one instant, and there at another. And you'll see it jumping about, or as we say, blinking. And so this device, very favorite device for astronomers, is called the blink microscope. And it's particularly sensitive because the eye is so automatically responsive to anything that flashes. That's why we use flashes for direction indicators on cars. And again, thanks to the skill of the BBC cameramen and engineers, we can illustrate the principle by looking at pictures of this painting of a Christmas lecture given here by Sir Lawrence Bragg when he was director. And the artist has deliberately blacked out one object in the one picture, which is there on the other. And you'll see there are an enormous number of things you could be looking at in that picture, and it would take a very long time and a great deal of painstaking work to say what is the difference. But those pictures have been recorded and stored by the BBC cameras, and the two pictures can now be flicked quickly from one to the other, and I think then, very quickly, you'll find down in the bottom right-hand corner, you will see there the small jar on the bench blinking at you because it's there in the one picture and not in the other. Now, without that blinking, it would take you a very long time to detect it, but there easily you can see it. Well, how far can we go with such methods when we apply them here? The answer is really very impressive. It is that supposing the Earth's orbit were reduced to something like this diameter, the precision of astronomical measurement is such that one could detect the difference in directions of light coming in from an object 3,000 miles away. Just off this baseline alone, it can be done. But, of course, it is a very tedious process, and although this gives you the distances of stars so far away that light would take more than 100 years to reach us from them, it is only a very small fraction of the stars that we know about. Only some 5,000 or so out of 100,000 million, even in our own galaxy. And after that, these trigonometrical methods break down. What we have to do is to study the stars in our local sample as close as we can, and this, fortunately, has enabled us to establish that there is very often a correlation between the spectrum of the light that comes from the star and the total amount of light that the star emits. And as a result, even at greater distances, if we can see stars of the same kind, we know how bright they are. And we can take their brightness or faintness as an indication of how close or far away they are. And there are still more interesting stars which do in fact vary, particularly the stars known as Cepheid variables, which rise and fall in brightness with a period of a few days, and the maximum brightness is very much linked with the period. We don't know why, but it is. And again, we can use such stars to go to much longer distances, out to more than 1 million light years, so that we can see them in bodies which we believe are like our own galaxy, but a long way further away, more than 1 million light years away. This is the closest of the famous ones, the Great Nebula in Andromeda. And so we then go to these to look at, to see how much light they emit, and typically they would be rather like our own galaxy, having something like 100,000 million stars in them, and so their full light power is something like that. And we can then see how far into space we can see them getting ever fainter and fainter, and the answer comes around here, that we can get out. You see, so Saturn, it takes about 400 minutes, something of that order. The nearest star, light is so far away, it's so far away that light takes 4.3 light years to get here. The furthest we can do by this technique, 150 light years. The diameter of our own galaxy is 100,000 light years, and the furthest ones that we think we can see appear to be of the order of 10,000 million light years away. Well, that gives you some idea of where we, as it were, how small we are in comparison with some of the things that we can see. But of course, we also know from a previous lecture how big we are compared with a micron or atomic diameters, or as we've seen in this lecture, or just mentioned anyway, the tiny nucleus of the atom, which is less than 1/1,000,000th of a centimetre across. Well, that's all I can say really about, as it were, our place in the physical world in terms of size. And I want now to talk about one or two of the other methods by which one can measure the distance to a distant object when you can't actually, as it were, stretch a tape measure out, or can't perhaps triangulate on it, but nevertheless you want to know how far away it is. And there are one or two very valuable properties which are worth knowing. One of the simplest, of course, which often I'm sure most of you have done, is to try and estimate the distance of a lightning stroke away from you, because you know that the light has travelled almost instantaneously, whereas the sound takes roughly 5 seconds to cover a mile. So all you've got to do is to observe the flash and start counting 1, 2, 3, and so forth, and it's a mile for every 5 seconds. What we have done there, in fact, is to use two different kinds of wave being emitted, light wave and sound wave. And the light wave is gaining on the sound wave all the time. But if we can tell when both of them pass us, we can work back as to how far away it must have been that they started. And here we have, in the lecture room, a demonstration of a miniature lightning flash, which will be made by this famous Wimshurst electrical machine. It will in fact be a fat spark rather than a true lightning flash, but the phenomenon is the same. It will emit both light and sound, and up at the back of the lecture room is a detector, both a photoelectric one and a microphone, and both of them we will try and record on the cathode ray tube here, so that you can see the two traces. The top one is the light flash, the underneath one is the sound, and if with luck we'll catch, it's a case of pure luck as to when the spark goes, as to the position when the cathode ray scan is. We're very unlucky so far. There's one, and you can see the light, when the light flash occurred and is recorded, and on the lower track you can see that about a 30th of a second afterwards, because it's only got 30 feet or so to go, you can see the noise being picked up by the microphone, and indeed there is a bit of an extra tail on it, because there is a bit of reverberation in the lecture room which the microphone is also picking up. Well, there is a very simple example, but a very useful example because it tells us so much about the structure of our Earth, is the fact that earthquakes emit several different kinds of wave. The first one, the one that travels fastest, and those of you who've done any physics and wave motion will know that there are two principal types of wave: the longitudinal wave, where the movement of any particle is in the direction of propagation of the wave, and the transverse wave, where the motion of any one particle is at right angles to the direction of travel. And they're the waves that go through the body of the Earth. Over the surface of the Earth, you can get two other kinds of wave. This one, which is known as the Love wave, nothing to do with rock and roll, but Professor Love was the man who first conceived of this kind of wave. And the one which is very common in earthquakes, and in fact does quite a lot of the damage, is this one, the Rayleigh wave, which is a ripple on the surface of the Earth, very much like the ripple on the surface of the sea. In fact, the motion of the particles is exactly the same. And if you get a seismograph recording a distant earthquake, you will find that the different waves come in at different times. And this shows two earthquakes which were recorded on one of our instruments in Aberdeen. And you can see that this pattern is a good deal more stretched out than that one. And in particular, the first kick in each of these is what we call the push wave, primary wave, the longitudinal push, which has come to us through the center of the Earth. Not through the center, but through deep through the Earth. We then get waves which have also come through the Earth itself, through the body of the Earth, which are transverse waves traveling more slowly. And then we get these Rayleigh waves traveling around the surface of the Earth, and they are coming in about here. I'm sorry that the picture isn't detailed enough to show you exactly what it is. But roughly, these waves, very roughly, travel at about 9 kilometers a second. These traveled about 3 kilometers a second. And there are 900 seconds between that and that, in this case, or 2,000 here, between the red and the blue. And from that, we can work out that this earthquake must have occurred about 5,400 kilometers away from Aberdeen. In fact, it was in Iran. Whereas this rather similar-looking earthquake, but more protracted, has come from a good deal further away, about 12,000 kilometers. In fact, it was in the Philippines. And so, in this way, you see, just by analyzing the records, you can tell fairly accurately the distance away the earthquake occurred. And if you have several observing stations, you can draw a circle around each one, and had the earthquake occurred on the surface of the Earth, and of course you have to do this in 3 dimensions and not just on a flat Earth, the circles should all intersect nicely in one point. Well, sometimes they do, but often they don't. And you find that each one tells you, each station tells you, the station is a bit further away than the spot on the surface of the Earth, which is at the center of the triangle when they cross. And the answer is that the rays from the earthquake have not come from the surface, but from some depth. And you can work out from the geometry the depth at which the earthquake occurred. And at once there is an interesting fact. We've never recorded an earthquake at a depth of greater than 700 kilometers. And the obvious inference from that is that at those depths of temperature and pressure, the Earth is sufficiently plastic so that all the movement that goes on in the crust can be accommodated by plastic flow in the body of the Earth and not by actual breakages and ruptures which result in the very sharp and very disastrous waves that are emitted from earthquakes. And if one looks at a typical region where you can plot time after time where the earthquakes are, and this is the east coast of Asia here, just north of Japan, and you'll find that the earthquake belt is running like that. The shallow earthquakes, which are the starred ones, are along here, and the deeper ones are progressively further west. And if one takes a section across there, like that, and looks through at that section, the next slide shows the picture that we get, that the earthquakes occur on a line running down at approximately 45 degrees into the Earth, no earthquakes after there, but the deep earthquakes being further displaced from here, and almost always you have a trench in the ocean and a raised arc of volcanoes, or sometimes is a whole mountain range like the Andes on the other side of the Pacific above, well above sea level, but quite often they're only an island arc, as we call them, with volcanoes there like that. And there's a sort of crumpling up of the, just as if you put your foot on the carpet and push it, you get this sort of effect. And the inference is that this part of the Earth's crust is in motion relative to that. The only accommodation is for one of them give way. This one is coming down here like that, gradually getting hotter and more plastic, as indeed this is. And after that point, any motion is accommodated by plastic flow rather than by actual rupture as you get nearer the surface, giving rise to earthquakes. There's one further method that I'd like to talk about, which, again, has the benefit of you're not having to go to the point where the source is in order to find where it is. And this started in World War I. It was the situation in World War I where, as you know, the fixed point, the front lines were almost fixed from month in and month out. And you were apt to be shelled by enemy batteries some distance behind the line. And of course what you wanted to do was to find where those batteries were so that you could ask your artillery to shell them in return. And of course if you could see the flash of the gun and on the other side and hear its report, you could do exactly what we've just been talking about. But the beauty of this method was that even if you couldn't see the flash, if you could merely hear the sound of the gun, you would get some idea of where it was. And this was called sound ranging, and again, it was Sir Lawrence Bragg, who was director here afterwards, who had a great deal to do with its development. And to give you an idea of how it works, we have a model here, and it works not only for sound waves, for any kind of waves, and in particular, radio waves. But for the moment, we're just going to imagine we've got a source of waves which are going to be emitted from some point on the Cherbourg Peninsula, which is here. And we'll need the lights down, because what I want to do is to have 2 volunteers to man the observing station. All right, you 2 then come. And what we're going to do, we'll have 2 observing points, you see, and you'll be listening, shall we say, to whatever's coming from here. Now, there's a circle of light here which will start to expand. And what we want to do is that we're going to pretend this is sound for the moment, and when the light passes you, you pretend you hear the bang, and you say to me, now, you see. And if you'll do exactly the same thing. And so, let me get this and see if I can. Okay, it's about to start. Now, the clock, we're happy with the, sorry? That's right. So here's the clock. And you see, when you say, you're going to look after this one, are you? Right. When this circle of light crosses that circle, it's about there, you say to me, now, and you say to me, stop, when the circle crosses there. Right, so now we'll start it. Oh, come on. Now we're going, you see. We're imagining this is a wave coming out from here like this, and gradually expanding, and we're getting near number 1.
No.
Right. Now, watch it. goes on and on, you see. And this could be a sound wave, or speeded up, it could be a radio wave.
Stop.
Like, you see. And we now see that it has taken 25 seconds longer to reach you than it did to reach you. So what we know from that is that the source must be somewhere such that the extra distance from here to there, as compared with there to there, corresponds to the distance travelled by the wave in 25 seconds. Thank you very much. Now, at first sight, that may not have helped very much, but in fact, it's done a very great deal, because it's removed an enormous number of places where that source could be. We know it must be on a line, somewhere on a line that is such that any point on that line is closer to the one observing post than the other by a constant amount. Now, many of you know, perhaps I don't know, is there time? That there is this famous curve, the ellipse, where if one does this, I'll start out here. You know this famous method of drawing an ellipse, like this, where one takes a thread and two pins and does that. And that works because the ellipse is the locus of points such that the sum of the distance of any one point on it to two fixed points is a constant. And that, which is also very useful in these some radar applications, has a sister curve, the hyperbola, where the difference between the distance for the 2 points remains a constant. So if I put my pen through any one of the links in the chain and pull it, it will feed out from the spring-loaded thread here equal amounts to each of these points. And as a result, I should get a curve. There we are, like that. If I can get it on the return journey there, like that, it will come round like that. And in fact, one can do one over here, like that, corresponding to whatever time distance it is that we know we've got. And indeed, one can, I just showed the two there, but we'll make a whole family like that. And any one of these curves is a point such that the difference in distance from here to there, from there to there, is exactly the same as it would have been from there to there and there to there. And so what we know at once, if we have these 2 points plotted on a map, we call these the foci of the hyperbola, the figure for the delay between the sound reaching the 2 observing points will tell us which of these hyperbolae we're on. And you might be interested to see the map which was used for our landing in France on D-Day in 1944, where we have 3 radar stations. We've only got 1 curve here, you see, but if you've got 3 stations, you can get, we might just show that if there's a moment. If you've got 3 stations, here are 2 of them, like that, and you take another 2, at least you take a 3rd station, so you've now got a pair of hyperbolae. You say the information from these 2 tells you it must be on that curve, the information from these 2 stations tells you it must be on that curve, and it must be somewhere in that region there. You see, oh, shall I bring this? Yes, that's better. Now you can see it there like that. And so you've got an actual location if you can observe the time differences at 3 stations. And exactly the same thing can be done with radio waves. And here you see with 3 radar stations, G stations, we call them like that, you can get the 2 crossing family of hyperbolae, and you can either send out pulses at the same time, 3 C stations, and notice the delay being received at only 1 point there, which is what we did, or the other way around. And you can, in this way, set up an imaginary grid over the surface of the Earth. Well, so much for that, because it's leading us into military measurements that I want to talk about next time. But to end with, let me introduce you to a very interesting effect known as the Doppler effect, which we can illustrate, first of all, because the engineers have recorded the sound of a police car siren, if we can have that. And as it goes past, you hear the drop in tone. Well, we can simulate that because the police car is sending waves to us, and if I transmit waves in imagination along this medium here, but we pretend this is the air carrying the sound waves to us. One. Oh, well, I've got to do it in time with the metronome. Well, I think you've seen enough now to see that the receiver hears exactly the same frequency as I'm transmitting. Now, if I am moving away from him, sorry, I have to get that one on there like that. You'll see he now has a lower frequency. This corresponds to a change in the sound. The sound is of a lower note. But let me now do, if I can, go towards him, and you'll see the problem rather increases for him. If I increase my speed like that, you can have quite a job. Well, you see, that is the Doppler effect, which enables us to measure speeds. And the beauty of it is that we measure speeds at any distance of objects that we can't actually get to. And it shows us that in our phase, the universe is expanding. Well, in the next lecture, I'll talk about applications of all these techniques to some of the problems we faced in the military field. Thank you.